All right, guys, let's take a look at our first problem here. We have a polar bear pushing a 7.5 kilogram object across frictionless ice with a force of 4 newtons. What is the net force acting on this object? So first thing we want to do is identify some important information in the problem. It tells us 7.5 kilograms. That's referring to the mass. It tells us a frictionless ice. So we know that there is no force friction happening in this problem. Then it tells us that there is an applied force of 4 newtons. Awesome. So I'm just going to go ahead and draw a free body diagram real quick because I love them so much. I know I have force gravity pointed down. I know it's on a flat surface, so I have force normal pointed up. These two are the same size. And then to the right, I have that applied force, which I know is 4 newtons. I don't need to draw a free body diagram, but I'm going to do it because it's going to help me figure out the problem in a sec. So the first question says, what is the net force on that object? Well, the net force on that object is just talking about is in the direction that the object's moving. So the net force in the y direction is 0 because the object's not moving in the y direction. But this is talking about the total net force, so that's taking into consideration the x direction as well. So the net force in the x direction would be equal to mass times acceleration in the x direction. Well, since we don't know the acceleration in the x direction, we can't solve for it this way. So we're going to have to solve for it by adding the forces that point to the right. So that would be force applied, and subtracting the forces that point to the left. In this case, that would be no forces. Again, why am I adding the forces that point to the right? Well, I'm adding the forces that point to the right because I would have an origin here, and up is telling me the positive y, and to the right is telling me the positive x. Positive x just means I'm going to add those forces. So now that I have my equation right here, I'm just going to plug my numbers in. I find out that net force in the x direction is just equal to force applied, 4 newtons. Next step, with what rate does the object accelerate? Well, if it's talking about acceleration, I'm going to have to look at my net force once again. And I find out that net force equals max, which also equals force applied. So in this case, I can say that m times a is equal to force applied. So if I'm solving for acceleration, I would just divide both sides by mass. And I find out that acceleration for this problem should be equal to my force applied over my mass. I plug in my numbers. I get 4 divided by 7.5. That gives me an acceleration of 0.53 meters per second squared. Next thing I want to do is figure out if the object starts from rest, how fast will it be traveling after 1.5 seconds? Well, if it's asking how fast something's going to be moving after a certain amount of time, that's talking about kinematics. So I'm going to have to use one of my kinematic equations from above to figure it out. So I would recommend, just to be safe, maybe go ahead and label your variables for kinematics like we used to back in the day. So we have dO, dF, VO, VF, A, and T. Initial distance would be 0. Final distance we don't know. Initial velocity would be 0 because it tells me that it's at rest. So that's telling me that VO is 0 meters per second. VF is what I am solving for, right? It's asking me how far it's moving. Acceleration I just solved for is 0.53, and time is given to me as 1.5. So since I have VO, I have A, I have T, and I'm solving for VF, I'm just going to go ahead and use a little pup. So VF equals VO plus A times T. I plug in my variables. I find out that VF is equal to 0 plus 0.53 times 1.5. I do the math, and I get VF is equal to 0.8 meters per second. Last step is just asking me to figure out how far the object will slide. Again, I have my variables here, so I can just go ahead and look for an equation that has dF in it and solve that way. I see up here that I have two options. I could either use Shaggy Cat or I could use Big Dog. I'm going to go ahead and use Big Dog. And Big Dog, remember, just tells me dF equals dO plus VOT plus 1/2 AT squared. I don't have a dO. My VOT is 0. Therefore, I just find out that dF is equal to 1/2 times 0.53 times T, which is 1.5 squared. I do the math and I get dF should be equal to 0.59 meters. Therefore, the box or the thing of cola would have slid 0.59 meters, and it would have ended up with a final velocity of 0.8 meters per second after 1.5 seconds. The acceleration on that box was 0.53 meters per second squared, and the reason for that was because the box felt a net force of 4 newtons. All right, guys, let's go ahead and get started with this next problem. A person with a mass of 82 kilograms stands on a scale in an elevator for some reason, who knows why. But from the bottom floor, the elevator accelerates upwards at a rate of 0.45 meters per second squared. So again, first thing we want to do is label our origin so we know what's considered the positive direction and what's considered the negative direction. So up, we're always going to say is the positive y direction, and then to the right would be the positive x direction. Because they're in an elevator, they're really only going up or down, so the y is the only one that we're concerned about. Next, we're going to take a look at the problem, and we see a person with a mass of 82 kilograms. So we see that this is talking about mass over here. And that says that they accelerate upwards at a rate of 0.45 meters per second squared. So that's talking about the acceleration of the person in the elevator. First question says, what is the net force on that person? Well, we know net force is equal to mass times acceleration. We just said that the mass of this person is 82 kilograms, and the acceleration is 0.45 meters per second squared. We solve and we find out that the net force on this person in the elevator should be 36.9 newtons. So it asks us, what is the person's weight? Well, by weight, we're talking about force gravity here. And we know that force gravity is just calculated by taking the mass times the gravitational pull. So we would find out that force gravity is equal to 82 times 9.8 because they're on Earth. We solve and we get a force gravity of 803.6 newtons. Now that we have force gravity, we want to figure out what the normal force read by the scale is. So this person's in an elevator, they're standing on a scale here, and the scale is pushing up on them. So it's applying a normal force to them. So if I draw my free body diagram, I have normal pointed up and force gravity pointed down. You can see that I made these two different sizes here. The reason being is that these forces are unbalanced. Why are they unbalanced? Because the elevator is accelerating. How do I know that force normal is bigger? Well, it's accelerating upwards. So it's experiencing a net force in the upward direction. So that means that our upward force of force normal is going to be bigger than our force of gravity. So let's take net force, set it equal to the forces that point up, force normal, minus the forces that point down, force gravity. Plug in our numbers. Net force is 36.9. Force normal is unknown. And force gravity is 803.6. Add 803.6 to the other side, and we get force normal is equal to 840.5 newtons. So moving along, it says after a moment, the elevator reaches a constant velocity. So constant velocity telling us that forces are balanced here. And we know that balanced forces are just telling us that the net force is equal to 0 newtons. It's telling us that it continues to move upwards, which is fine because it's moving at a constant velocity. What is the net force on the person at this time? Well, we already answered that. We know that the net force on this person should just be 0 newtons. And the reason being, it's moving at a constant velocity, so the forces are balanced. If we have balanced forces, our net force is 0. Another reason is because constant velocity is telling us that acceleration is 0. Therefore, net force is equal to mass times acceleration. If acceleration is 0, this whole thing turns to 0. Next question, what is the normal force read by the scale? So the way that we can figure out the normal force read by the scale is drawing another free body diagram. We show normal force points upward. It says that it's moving at a constant velocity, so these forces should be balanced. So force gravity should be the same size and point down. We're going to take our equation, net force equals the forces that point up, force normal, minus the forces that point down, force gravity. Plug in our values. Net force is 0. Force normal, we don't know. And force gravity is still mass times gravity, so it should still be 803.6. Add 803.6 to the other side, and we find out that force normal is just equal to force gravity, which is 803.6. And the reason being is that it's moving at a constant velocity, so the forces are balanced here. So again, force normal is just equal to force gravity. Main reason is because there is no acceleration. All right, taking a look at the next part, it says as the elevator reaches the top floor, it begins to slow down. The scale reports the person's normal force as being 774.9 newtons now. What is the net force acting on the person? So let's go ahead and draw a free body diagram of this. We show normal force pointing up, and then we're going to show gravity pointing down. You're going to see that I'm making gravity bigger here, and I'm making gravity bigger because it's telling me that it's slowing down. It also tells me that the elevator is still moving up, so I know that the velocity is pointed upwards, but the acceleration is pointed down. Since the acceleration is pointed down, that means that the net force is going to point in the downward direction. Acceleration and net force point in the same direction. Therefore, to figure out what the net force is, I'll just take my equation like I did before. Net force is equal to the forces that point up, force normal, minus the forces that point down, force gravity. I find out that net force should be equal to force normal, which is 774.9, minus force gravity, which we said above was 803.6. Force gravity still is the same because force gravity is just mass times gravity. Neither of these two things has changed in the elevator. We still have the same mass and we still have the same gravity. So we're going to go ahead and add those together, and we find out that our net force should be negative 28.7 newtons. The negative net force is just confirming what we already know, and that's that the elevator is slowing down because it's experiencing a negative acceleration. We're going to find out what that acceleration is right now. So net force is equal to ma. To figure out acceleration, I'm just going to divide by mass. And I figure out that acceleration should be equal to net force over mass. Therefore, if I plug my numbers in, I get negative 28.7 divided by the mass. The mass of this person, if you recall, was 82 kilograms. So if I simplify and solve, I find out that acceleration should be equal to negative 0.35 meters per second squared. So let's go ahead and take a look at our next problem here. It says a person pushes a 5 kilogram object to the right with a force of 24 newtons. The force of friction between the object and the ground is 15.5 newtons. So here's some important information that we should highlight. 5 kilogram object, that's talking about the mass. Pushes to the right with a force of 24 newtons, that's talking about a force applied. And the force of friction between the object and the ground is 15.5 newtons. That's talking about force friction there. Our first question asks, what is the net force in the x direction? Well, before we answer any of these questions, we're going to need to go ahead and draw a free body diagram. Here's our origin, and we're going to show that up is the positive y direction and to the right is the positive x direction. I know I do this every time, but it's always good to do it just in case. Here's my object. So the forces that are pointing down on the object would be force gravity, because force gravity always pulls objects downward. We can see that this box is on a flat surface here, so it's going to have normal pointed up from that surface. Next, it's saying that it's being pushed to the right, so we're going to draw a force applied to the right. It tells us that force applied is 24 newtons, so I'm just going to label that in here just because, no reason. And then to the left, we have force friction, which is 15.5 newtons. Since force friction is smaller than force applied, I'm going to make this arrow smaller, and I'm going to label this one also. All right, so now that I have my free body diagram set up, I can just go ahead and solve for the net force in the x direction. I see that net force in the x direction is equal to the forces that point to the right, force applied, minus the forces that point to the left, force friction. I plug in my values here. I get net force in the x direction should be equal to 24 minus 15.5, and I get a net force of 8.5 newtons. So I'm going to go over here, write my net force of 8.5 newtons. Next, it says, what is the net force in the y direction? Well, the net force in the y direction, we just have to do the same thing. So we take our forces that point up, force normal, minus our forces that point down, force gravity. So we don't have the values for these, and we could figure them out, which I'm totally okay with, but we also can just look at the problem and figure out what the net force in the y direction is without having to do any math. What? This box is not experiencing any acceleration in the y direction. Therefore, it's not going to experience a net force in the y direction. So I know that these two forces, normal and gravity, are balanced. And because they're balanced, the net force is just 0. How do I know that they're balanced? Well, like I said, they're balanced because the box is not accelerating in the y direction. So our next question says, what is the acceleration of the object in the y direction? Well, net force is equal to ma. If we don't have any net force, we don't have any acceleration. So the acceleration in the y direction should just be 0. Let's go ahead and use that equation to figure out the acceleration in the x direction. Net force in the x direction is equal to mass times acceleration. So if we want to solve for acceleration, we're going to divide mass. And we find out that acceleration is just equal to net force in the x direction divided by mass. Go ahead and plug in our numbers here. 8.5 for net force and 5 for mass. We find out that acceleration in the x direction should be equal to 1.7 meters per second squared. Next, we want to figure out what the weight of the box is. Well, the weight of the box is just equal to the mass times gravity. In this case, the mass of the box is 5 kilograms. It gives us that answer in the problem, times gravity. Gravity is 9.8 because we're on Earth. So all we have to do is just multiply these two together, and we find out that the weight should be 49 newtons. Our last part, it asks us to find out what is the normal force on the box from the ground. Well, there's two ways to figure this out. The first way is to take our net force equation in the y direction, add the forces that point up, and subtract the forces that point down. Go ahead and solve for normal force by adding force gravity over to the other side. We find out that force normal is just equal to net force in the y direction plus force gravity. Net force in the y is 0, and force gravity is 49. So we find out that force normal is just equal to 49. The other way we could have figured that out is from our free body diagram up here, noticing that force gravity and force normal are the same size. And the way we knew it before was that we aren't experiencing any acceleration in the y direction. So we know that these two forces have to be balanced. If these two forces are balanced, then we can say that force normal should just be equal to force gravity. A person pushes a 6.5 kilogram object to the right with a force of 19.5 newtons. The box moves at a constant velocity. So 6.5 kilograms, that's talking about the mass here, to the right with a force of 19.5 newtons, that's talking about a force applied. And some really important information is saying that it's a constant velocity. So that's going to tell us that we have balanced forces here. And it's also going to tell us that the acceleration is equal to 0. Since there's no acceleration, that's telling us that our net force is equal to 0 as well. This is all really important information that we'll get to later on in the problem. Let's go ahead and set up our origin. We know that up is the positive y direction and to the right is the positive x direction. Here's our box. We know that it's experiencing a force gravity pulling it down. It says that the box is being pushed to the right, which means that it's not experiencing any acceleration in the y direction. So we know that force normal should be the same size and pointed up as well. We know that there's a force normal because there's a surface right here under the box that the box is sliding on. Next, we have a force applied being pushed to the right, and that force applied is 19.5 newtons. We also know that there's a friction force coming back from it. And we know that it's moving at a constant velocity, so that means that our force friction should be the same size as our force applied. So now that we have our free body diagram drawn, we're going to go ahead and answer these questions over here. What is the net force in the x direction for this situation? Well, I just told you it's moving at a constant velocity. Because it's moving at a constant velocity, acceleration is 0. Because acceleration is 0, we know that net force equals mass times acceleration. If this acceleration is 0, then net force has to be 0. So our net force is 0 newtons. What is the force of friction? Well, since our net force is equal to the forces that point to the right, force applied, minus the forces that point to left, force friction, we can go ahead and figure that out. So if we solve for force friction, I add force friction over to the other side and subtract net force. I find out force friction is equal to force applied minus the net force in the x direction. I plug in my values, I get force friction should be equal to 19.5 minus 0. So force friction is just equal to 19.5 newtons. What is the net force in the y direction for this problem? Again, the box is not accelerating in the y direction, so the net force in the y direction should just be 0. Same idea as before, how we said that net force is equal to mass times acceleration. Since there's no acceleration in the y direction, there's no net force. What is the acceleration of the object in the y direction? Again, if the net force is 0, acceleration has to be 0. What is the acceleration of the object in the x direction? Same principle. If net force is 0, acceleration has to be 0. We also know that acceleration is 0 here because it told us that we are moving at a constant velocity in the x direction. In order for us to have a constant velocity, it means that we cannot be experiencing any acceleration. So that's why our acceleration is 0. What is the weight of our box? Well, we know that our weight is equal to mass times gravity. We know the mass of this box is 6.5 kilograms, and we know the gravitational pull on Earth is 9.8. So we multiply these two together, and we find out that the weight of this box should be equal to 63.7 newtons. Now that I know what the weight of the box is, I can figure out what the force normal is on that box. Like we said before, the net force in the y direction should be equal to the forces that point up, force normal, minus the forces that point down, force gravity. So if we're solving for force normal, I can go ahead and add force gravity over to the other side. I get net force in the y direction plus force gravity. Therefore, the normal force is equal to the net force in the y direction, which is 0, plus force gravity, which is 63.7. That just tells us that our normal force is equal to force gravity. So normal force is 63.7 newtons.